x and z, that's negative 30 e to 3, 10 e to 6. And by putting that in calculators, we got 0.003. Oops. Doing the same what we did for x. So string of y times length of y. We have 0.003 times the length of y, which is, by looking at graph, 4 inches in our cases. And that's 0.012 inch long. Now the last thing is string z, which again is 0 first, minus the Poisson ratio of water, sigma of y, negative 40 e to 6, divided by 10 e to 6, plus z, which is negative 30 e to 3, divided by 10 e to 6, getting negative 0.003667. And do the same with x and y, so do the same with z. If we change the lengths, it will be this. Sorry guys, times 2, as you can see right here. So that will give us negative 0.00733 inches. And that's 0.00733 inches shorter. So that marks the end of this video. I hope you guys find it helpful. If you guys find it helpful, please subscribe, like, and whatever. And I do have Patreon, so support will be great. And see you guys next time. Hello everyone, welcome. And we're going to solve our problems. So here's some figures. We know A, we know B. And based on what the problem says, the B is displaced 12 millimeters. And it says we need 19 kilonewtons, and that force is 1. So we know that the P is 19 kilonewtons. And we know that displaced since 12 millimeters means that the change in length, in this case, is 12 millimeters. And obviously, we know A and B, which is given in the problem. So if you read this for the first time, you might not know how to solve this problem. So what we're going to do is, assume we don't know how to solve it, we're going to write what we know, the three equations. So we know that the tau is equal to P of A, and tau is also equal to gamma times G, which is our shear calculus. And we know that gamma in this case is equal to transient length divided by T. Now, what is T in this case? We're about to figure it out. So by looking at this, we can see that to get our shear stress, which is tau, we need to have an A. So A in this case is actually 500. Oh, my bad. This is 2, not 5. 200 times CP. So in this case, it's 220. So that's give us 44000 meter squared, and that's equal to 0.044 meters squared. So now we got our area, we can plot our shear stress, which by using P divided by A, so that's 19 e to 3 newtons, divided by 0.044 meters squared. Now, Newton divided by meter squared gives us Pascal. So we got 4318.18 pascals. By moving decimal places 3 to the left, we get 431.8 kilopascal. And that's our tau. And based on the tau, the G is given as tau divided by gamma. So we need to know gamma. And that the gamma in this case is transient length, which we already know, divided by T. Okay, so T is our height in this case. So it's A. So what we're going to have is transient length, which we talked about earlier, is 12 millimeters. The height, which is A, in our case, is 30 millimeters. So by doing so, what we end up is 2 over 5, or 0.4. And that's units. Plug in our G, so kilopascal is equal to 3 pascal, divided by 0.4 in this case. What we end up is 1.0795 e to 6 pascal, and that's equal to 1.08 megapascal. So hope you guys find this video helpful. If you do, please make sure to thumbs up and support me on Patreon if you can. See you next time. Hello guys, welcome. So I already did something right here for this problem, and feel free to react what I did. So basically, it says that determine the amount of the normal stress sigma z if the change in length of z dash is not 0. So we know that the change in length of z is 0, and that implies that the strain in z is 0. So if we substitute z here for zeros, everything is given. So that will give us sigma z as 40 ksi, and we basically got everything for string x and string y, and to find the transient length of x, we just use our transient length formula for string x and length x. For string y, we also use our string formula, which is string y times length y. Now, length x, length y is giving a problem, so we can find out the string x, string y, just plug in into our formulas, and we'll get answers. So, one trick here is that I would like to talk about, and I mentioned in the last video, is that when you see the graph, as you see in this case, in 3D, you use the equations right here, the string x, string y, string z. It's not on 3D. Then we use the simple formulas, which means that the string x equals to translate x divided by length. String y is equal to string length y divided by the height. In this case, this line right here. And string z is equal to basically elongation z divided by length of z. So in this case is this thing right here. I'm taking it out. So this is used when the bit is not 3D. And this is used when the bit's got x, y, and z. So I just want to confirm that and talk about that in the last video. And the last important thing I want to mention is that when you see these progressing y is after the compressions. So when you start tuning the y values, as you see here, is 100 KSI, you want to make sure you put a negative. This is in compressions. And that will solve basically every problem to encounters that related to this problem. So I hope you guys find this video helpful. And I think you guys can solve this right away, just plug in numbers. So that's just something good. And feel free to support me on Patreon if you can. And see you guys next time. Welcome. So here's our problem. We know that the moment is quite for this way, and we define the moment stress at point A, B, D, E, and F. So start from there. How do we find the moment stress? So we're not going to use our typical moment stress, which is P over A. In this case, the moment stress we're going to use is negative F times Y divided by I, which is moment inertia. So let's start by finding moment inertia. So moment inertia is equal to 1 over 12 BHQ. So B is where the z-axis goes, so it's 70 in this case. So that'll be 1 over 12, 70, and height is the y. So in this case, it's 30. So that's about 1.7500 millimeter to power 4, then that equal to 1.575 e to the negative 7 meter to the power 4. So now we can use our formulas. Since we know I and we know m, the problem with here is what is the sign of m, and that's pretty much what we're going to have problem with. So in this case, we have a ground beam, or like in this case, it's going to be, the moment's going to be a negative. We have a smile, it's going to be a positive. So as you can see, in this case, when the moment is applied, the beam is the case number 1, so the moment is going to be the negative. So we have a negative. So the y is the distance from the centroid, which is the negative, to the distance of the point we're trying to find. So for A, that will be minus, and for m, that's negative 1.2 e to 3. Now the distance is above, so it's going to be positive. So that's going to be 0.015 meters divided by I, and we're trying to use meters here, so it's 1.575 e to the negative 7 meters per 4. They give us 1.14286 e to the 8 pascals, or 114.3 megapascal in tensions. Now I'm not going to finish all points, but I'll do B, which is below our centroid. So we're going to do stress of B, that's equal to negative 1.2 e to 3, and our distance is, as you can see, it's 15, so this is 10, so let's do 2 minus 10, or in meters, negative 0.005 in meters, and our I stays the same. So by doing that, we get negative 3.8095 e to 7 pascals, or negative 38.1 megapascals, and it's 38.1 megapascals in tension, not in compression, sorry, this is negative. So now you can do the same thing for D, which is above, which is the Y, it's going to be 400 changes. For E, since it's on the same line, it's on centroid, the same height, it's going to be 0, and F is the same case as B. So I hope that helps, and see you guys in the next video. Hello everyone, so welcome. Today we're going to solve a homework 14, which is basically given our figures right here. And like a beam, they need to find the maximum potential and maximum compressive force in portion B, C's. So, right here. So, as you can see, we need to find a y bar first. So, how do we find a y bar? So, y bar is equal to summation of y times A and summation of area. So, for this, that's 30 times 600. And how do I get this numbers here? Because I cut, make a cut here and here. So, this is C, or you can say it's base, and here's Y, or you call H. So this is 10 times 60, which is 600, and Y bar is half of 60, so 30. And the second one, that's 5, 300 for the middle section. And for the third sections, it's the same thing as the first section. So that's 600 plus 300 and plus 600. So Y bar, based on this, is 25 meters. So now we got our Y bar. to find the maximum temperature and maximum pressure stresses, we need to use our formulas, negative my divided by I. So the I is the summation of the 1, 2, 3, the 3 parts we have. So that will be 1 over 12 PHQ plus 8 dy squared. It's 8 dy squared, don't forget about that. So for the first part, that's 2, 3, that's going to be 1 over 12, 10 times 62 plus 630 minus 25 divided by squared. So that's 19530 millimeter per For the second part, which is this part here, that is 112, 30, 10 to the cube, plus 300, 25 minus 5 cube squared, and that's 122500. So we're pretty much going to have, for I total, we're going to have the I1 plus I2 plus I3, and I3 is just I1. So if I add them together, we get 1512500 millimeter to power 4, or 5.125 e to the next 7 millimeter to the power 4. Okay, let's zoom out. Now we get I. And we need to find M. This is the last one, you know. So to find M, he says to find M quotient BC. So it's kind of in between B and C. So therefore, the three-line diagram, we have a AY, and you can see this is a if you cut this is a symmetric. So this is going to be a 10 kilonewton force, and we know here's a 10 kilonewton force applies. So it'll be a 10 kilonewtons downwards. And there's a shear stress once we cut it, and there's a moments. So summation of the moments at point A should equal to 0. But that said, that's going to equal to a negative 10 e to the 3 newtons times 0.15 plus moments is equal to 0. So only the force up here, B here affects because the A go through point A, so it's not affecting. So the moment is 1500 Newton meters. So now we can use to find maximum tension and maximum compression. So that'll be negative 1500, which is fine, times negative 0.025 for the tension, and that's divided by 5.125 e to the next 7, and that's 73.2 megapascal in the tensions. For the compressions, still same thing, but the exact distance is different, just 0.035 over 5.125 e to the negative 7. So that's negative 402.4 megapascal, or 102 megapascal in compression. So hope that helped you guys. If yes, thumbs up, subscribe, and I'll see you guys next time. Welcome. So we got a offset, which is applied to revenue, and an offset is 0.75, written average 0.08 gas rated. So based on this, if we are given that the out diameter is 0.75 inches, and the wall thickness is 0.08 inches. Therefore, the inner diameters is equal to the out diameters minus 2. But that said, the 0.75 minus 2 times 308, which is 0.59 inches. And for area, things are going. The outer meters, this will be power for the outer 2 power 2 minus the inner power 2. So I1 for 0.75 squared minus 0.59 squared is 0.1684 inch to 6. Now we have to compute the maximum stress. So that's going to use the P array. So it's P over 0.1684. But it's not yet. It says after the offset must not exceed the 4 times the original stress. So if the offset stress now is 4 times that, what we can say is the original stress is equal to 4 times the offset. For the offset stress is quite different than the stress here, because the offset stress is got an outcome, so it's plus minus P, A plus minus over 3, Y, 9 in this case. So on the Y bar, that's 0.75 by 2, that's 0.375 inches. Now the question is, how are we going to find the MC? So to find MZ, we record on the last video right here, when you can watch it, is we want to cut the row. So pretty much, when you cut the row, is after cut the row, we have like this A, we have a moment, and we still have a P. So what that means, if we do the sum of moment at point A, then the moment is equal to HP, where H is the height. So, and IZ is IR R4 divided by 4, which is R4 0.375 over 4, and minus 0.59 divided by 2, which is the half meter, and there's R4, that's 0.009 by 83 inch to 4. So that says now we got everything to find second components here. So that is P over 0.1684, and we call it P, as you can see, is in tensions as positive, and the moment is H 0.375, which is right here, and 0.009583. So this whole thing is equal to 4P divided by 164. So that's 1 over 0.1684 plus H times 0.375, 0.00953. I just basically cancel P from both sides. So that says H is 0.455 inches. So hope that somehow helped you guys. Leave in the comment section if you have any questions, and I'll see you next time. Thank you. So today we're going to do this problem. Feel free to do these problems. I'll be getting started right away. So let's draw like a relay diagram. So we got a rod extended from here. The little rod is we want to have a cut, just like we did in previous examples. So how are we going to cut this? In this case, we're going to cut horizontally. So here's B, here's A, and D is right here, and we have D. So the cut piece will look like the following. This horizontal line should use this line right here, and then we know this is 1 inch, and the height here is 0.8 inch, the whole thing. So let's find I. So I is 1 over 12 BHQ. B in this case is 4. Height is 0.8, so that's 0.04267 inch out 4. Now cross-sectional area is just 0.8 times 1, which is 0.8 inch squared. And we know the stress is maximum at point A, and right here. So that's going to be half of the 0.8, so 0.4. And the length is 1.5, which is the actual right here, minus 0.4, so that's 1.1. Now, you know, when we cut it, there's a moment. So moment in this case is the P times the length as usual. So that's P times 1.1 or 1.1. To find the stress at point A, the magnitude, as you can see, the P is in compression, so let's say the P over A minus my the I over magnitude, we can write as positive, so that's 1.1 P, Y is 0.4, and the other is 0.04267. So Q of A, not Q, but stress of A, in this case, ends up being 11.5625 P. So this is our stress at A, and it says the maximum, Q max is 10 KSI. In other words, this whole thing here needs to be equal to 10 KSI, which is converted to 10 to the e to 3 PSI. So if I divide both sides, we got 865 pounds. Okay. So hope that helped you guys solve these problems. Leave in the comment section if you have any problems, and see you guys in the next video. Welcome. So it's been a quite long time since I upload videos about stress materials. I'm back. Because not much what you're gonna do. It's lay down there and pile out your skin. Sort of lazy, and I don't want to continue your tutorial series. So I'm not speaking. We got from here. A word ID is constructed by going 3 boards together like I'm showing here. And we know that B, which is equal to 1.5 kips, is applied to the beams. And we left find the shear stress in the glue joints and the maximum shear stress in walls. So to solve this problem, we gotta know what is shear stress. So shear stress, which has the symbol tau, is divided by BQ divided by IT, where T is the length of the cup. So if you look at this equations, you know that we need I. So a quick way to solve this I right here is use the total I minus the 2 small i's right here. And that's what we're gonna do. So the equation of I is 1 over 12 BHQ equals to 1 over 12. So the base of the outside ones is 8 inches. So we got 8, and the height is also 8 inches. So let's see the outer ones. And remember we said we need to minus the 2 inner ones right here. So you can actually combine the 2 inner ones into one expression, and that's 1 over 12. The base is 3 plus 3, 6, and the height is 4 cubed. So by doing that, our I is 309.33 inch power 4. And if we plug that into our equations up here, that tau is equal to BQ over IT. So B is 1.5 cubes, given the problem. Q is AY. So area will be exert has the